Good day, Math Buddies! Sir Sherwin here, your math instructor. For today's video, we will be discussing all about quadratic inequality in one variable. And of course, we will determine the solutions of our quadratic inequality. So to be updated with our new content, please don't forget to subscribe and hit the notification bell. First, let's try to define a quadratic inequality. It is a mathematical inequality in the form ax squared plus bx plus c greater than 0, ax squared plus bx plus c less than 0, ax squared plus bx plus c greater than or equal to 0, and ax squared plus bx plus c less than or equal to 0, where a, b, and c are real numbers and a is not equal to 0. With this, let's try to determine solutions of a quadratic inequality in one variable. Supposing our quadratic inequality is given, and that is x squared plus 4x minus 21 greater than 0. With this, to determine the solutions, first step that we need to remember is that we need to write our quadratic inequality in its corresponding quadratic equation. This means the inequality symbol will be changed into equal sign. And this leads us to x squared plus 4x minus 21 equals 0. Again, we need to change our inequality symbol to our equal sign to make this one a quadratic equation. We've learned that there are 4 methods used to solve for the roots of a quadratic equation. It can be extracting square roots, factoring, completing the square, or using a quadratic formula. So those methods will really help us determine the solutions of a quadratic equation. But for this example, allow me to utilize factoring in determining for the roots. So let's try to solve for the roots. So our trinomial has possible factors quantity x plus 7 times quantity x minus 3. Then apply zero product property as we set each factor equal to 0. Then let's solve for the roots. First solution is negative 7 and the second solution is equal to positive 3. And after we determine the solutions, next thing that we will need to remember is to draw the number line. What's the purpose? It is for us to locate the roots 3 and negative 7. So we'll try to draw a number line. And of course, let's try to write 0, 1, 2, 3. And of course, right of positive 3 are numbers that are considered our positive numbers or the positive infinity. Going to the left of zeros are negative numbers. So we have negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. Of course, we have negative 8 here. And of course, we will have the negative infinity. Of course, going to the left of negative 8 are numbers negative 9, negative 10, and so on. So again, we will try to locate our solutions 3 and negative 7. So it is for us to locate 3 and negative 7. This time, we will apply the concept of hollow or solid circles. We will utilize a hollow circle because our inequality given is greater than. So utilize hollow circles if our symbol are greater than or less than. But if our inequality symbol is greater than equal to, or less than equal to, we will utilize the solid circle. And that is the shaded one. Alright, so let's try to have a hollow circle in this case. After we locate our solutions, we notice that these roots or solution divide our number line into 3 intervals or 3 parts, 3 regions. So we have the first region, this one. This is our first interval. The second interval is between negative 7 and positive 3. So we have this as our second interval. And of course, we have the third one, the third interval. So again, our roots or solutions divide our number line into three intervals, three regions. With this, let's also create our compound inequality in our intervals. Let's try to create our intervals. So we have three intervals. Okay, so first interval represents points between our negative infinity and negative 7. So for our first interval, our compound inequality will be x is greater than negative infinity but less than negative 7. Meaning to say, all points that is between our negative infinity and negative 7 are all points or solutions part of our first interval. For our second interval, these are the points between negative 7 and positive 3. So our compound inequality will be x is greater than negative 7 but less than positive 3. So this would be our second compound inequality. Third, for our third interval, this is the region that composed points or solutions between positive 3 and positive infinity. This includes 4, 5, 6, 100, million numbers that is considered positive. So our third compound inequality will be x is greater than positive 3 but less than positive infinity. The purpose why we are creating these intervals is that we will utilize this in testing our solutions of quadratic inequality. X squared plus 4x minus 21 greater than 0. After we create our intervals, we will now proceed to testing. So, what will we test? In testing, we will utilize these intervals and choose one point present in this interval to test if it is true or false using our quadratic inequality. This means for our first interval, these are numbers between negative infinity and negative 7. Of course, we can choose any numbers between negative 7 and negative infinity. So if I'll choose negative 8 and you choose negative 9 and others choose negative 10, still you will derive with the same conclusion. So for me, allow me to utilize if x is equal to negative 10. Negative 10 is a number present between negative 7 and negative infinity. So what will we do with negative 10? So this negative 10 will be substituted to our quadratic inequality. X squared plus 4x minus 21 is greater than 0. So substitute all x by negative 10. So this means we will have negative 10 squared plus 4 times negative 10 minus 21 greater than 0. So here, we have negative 10 squared, we have 100. 4 times negative 10, we have negative 40. And copy minus 21 greater than 0. Combining 100, negative 40, and negative 21, we have 100 minus 61, which leads us to 39. 39 is greater than 0. Of course, 39 is greater than 0, and it says that the idea is considered to be true. So here, our first interval satisfies our quadratic inequality. So allow me to label our first interval as a true solution. So let's try to test our second interval. And again, our second interval are solutions that is present between negative 7 and 3. So again, we can choose any number that is present between this interval. So I can choose 2, you can choose 1, you can choose, others may choose 0. So it's up to them. In this interval, let's use x equals 0 because 0 is present in our second interval. So substitute 0 in our quadratic inequality to check if they are solutions or not. So here, we will have 0 squared plus 4 times 0 minus 21 greater than 0. So we will have 0 minus 21, that is negative 21, greater than 0. Of course, any negative number is less than 0. In this case, negative 21 is considered greater than 0, and this idea is considered to be a false statement because negative 21 is not greater than 0. This time, let's try to label our second interval false. Let's also test our third interval. And in this case, it is a number between 3 and positive integers. So, allow me to utilize x equals to 10 because 10 is present between 3 and positive infinity. So, here, we will substitute x by 10. So, we will have 10 squared plus 4 times 10 minus 21 greater than 0. So, we will have 100 plus 40 minus 21 greater than 0. So 140 minus 21, the result is 119 greater than 0. Of course, 119 is greater than 0, and that leads us to a true statement. So we will have to label third interval true. So here, if we notice, the first and third interval satisfies our quadratic inequality, and it gives us a true solutions. So this means we will shade the first interval and the third interval. And this signifies that all points present in our first interval and third interval are all solutions of our quadratic inequality. And for our conclusion, we can state that the solutions of our quadratic inequality x squared plus 4x minus 21 greater than 0 are x less than negative 7 and x greater than positive 3. This time, let's try to have our second example. Our second inequality is x squared minus 6x plus 8 less than or equal to 0. So first step is that we need to write our quadratic inequality in its corresponding quadratic equation. This means inequality symbol will be changed into equal sign. So this leads us to x squared minus 6x plus 8 equal to 0. That will be the easiest step. Second, we will solve the roots of our quadratic equation. In this case, allow me to utilize factoring. So by factoring, possible factors of this trinomial would be x minus 4 times quantity x minus 2 equals 0. Then we will solve for the roots using the zero product property. So we will set each factor equal to 0. And this time we can determine our solutions. X is equal to positive 4. And second solution is x equals positive 2. After we determine the solutions or roots, next thing that we will do is to draw a number line. So we will try to draw a number line as we locate positive 2 and positive 4 on it. Of course, we have 0, 1, 2, 3, 4. And of course, we have positive infinity right after positive 4. And of course, left of zeros are negative numbers. We have negative 1. And of course, we will have the negative infinity. So again, let's try to locate our solutions 2 and 4. So we have 2 and 4. And remember in our first example, if our inequality symbol is less than or equal to, we will have our solid circle. So in this case, circle will be shaded. So we'll try to shade our circle. This means 2 and 4 will be part of our solutions of our quadratic inequality. So here, we notice that our solutions 2 and 4 divide our number line into 3 regions or intervals. So we have 3 regions, 3 interval. This includes numbers between negative infinity and positive 2. This would be our first interval. Numbers between 2 and 4. This would be our second interval. And numbers between 4 and positive infinity as our third interval. To write our compound inequality for our first interval, we can say x is greater than or equal to negative infinity, but less than or equal to positive 2. For our second interval, our compound inequality would be x is greater than or equal to positive 2, but less than or equal to positive 4. And for our third interval, our inequality will be written as x is greater than or equal to 4, but less than or equal to positive infinity. After we create our interval, it is for us to test this interval. So in testing, again, we will utilize our given quadratic inequality. So to test our first interval, we will choose one number that is present in our first interval. So if this would be our first interval, we will utilize any number that can be present in this region. Here, if x is equal to 0, so substitute all x by 0 in our quadratic inequality. So we have 0 squared minus 6 times 0 plus 8 less than or equal to 0. To simplify, that leads us to 8 less than or equal to 0. The idea is considered to be a false statement. So we will label this one as false because it doesn't satisfy our quadratic inequality. This time, let us try to test our second interval. And in testing our second interval, we will utilize point that is present on second region. So we will not use 2, we will not use 4, but instead numbers between 2 and 4. In this case, we will let x equal to 3 and substitute all x by 3 in our quadratic inequality. So we will have 3 squared minus 6 times 3 plus 8 less than or equal to 0. So 3 squared, that is 9. 6 times 3, that is 18. Plus 8 less than or equal to 0. To simplify, 9 minus 18 plus 8, we have negative 1 less than or equal to 0. Of course, negative 1 is less than 0. That means the idea is considered to be true solution. And lastly, for our third interval, we will utilize any point that is present at our third interval. And in this case, allow me to use x equals 5. So substitute all x by 5 in our quadratic inequalities. We have 5 squared minus 6 times 5 plus 8 less than or equal to 0. So to simplify, we have 25 minus 30 plus 8 less than or equal to 0. So we have 3 less than or equal to 0. In this case, 3 is less than or equal to 0. The idea is considered to be false. So one good idea that we need to remember, if our first interval is false, it also justifies that the third interval will lead us also to a false statement. And, of course, the second interval will be the only interval that is considered to be true. But, if our second interval is false, it follows that our first interval and third interval are considered to be true. What do we mean about this one? Because our second interval is a true solution, we will shade this region. And that means all points that can be found between 2 and 4, including 2 and 4 itself, are solutions of our quadratic inequality. Therefore, our solutions can be stated as the solutions of x squared minus 6x plus 8 less than or equal to 0 are all points present between 2 and 4 and 2 and 4 itself. And we can write it in our compound inequality x is greater than or equal to 2 but less than or equal to 4. There you have it. Hope you learned something new today. God bless us all.